Hi there and welcome back to Triplicate and part 12 of the synthesis tutorial, and this is the second part of us looking at filter enhancements. Now this is going to be second of three looks at filter enhancements, and none of these are things I've actually implemented in synthesizers. They're just investigations I thought I'd put on the end as a starting point. And the last time we looked at trying to make our filter a bit warmer, and we produced some interesting results, but it was certainly no Mini Moog or TB303 when we'd finished. So this time we're going to take our filter and see if we can configure it to produce any more interesting results. So let's look at what we've got. Okay, so we have at our disposal two 12 dB per octave low pass filters, and what we've done with them so far is used one to give a 12 dB per octave filter, and we have used the two of them in series to give a 24 dB octave filter, both low pass. So what happens if we put them in parallel? So this one we can scale the amount coming out of it. So initially let's look at using this one as a low pass and this one as a band pass. Okay, so let's consider if we can do something with this for the attack sound of our synthesizer sound. So a traditional synthesizer will start off with a spectrum like that, and that's the resonance there, and over time we'll go down to a spectrum more like that. And what happens here is the cutoff frequency is being lowered by the envelope, so that gives the traditional synthesizer down, 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 down sound. Whereas in say an acoustic instrument, a plucked instrument like a guitar, more likely to happen is this: we will have initially say a spectrum like that with more than one peak, and over time those peaks will stay where they are, but the higher one will decay. So we will get draw this something like that. So the lower peak has not changed with frequency, the cutoff frequency has not changed with time, just that peak has gone, and that's more a ding sound, more like a bass guitar sound, whereas that is a ding ding. And in addition, what can happen is when it starts, the energy in the string is in the high frequencies where it's plucked, and it sort of transfers to the lower frequencies over time. I will look at this in a future video. So the lower frequency actually doesn't start immediately, whereas the higher frequency does. There is a sort of the lower frequency here, this peak ramps up with time. I hope that makes sense. So the low pass filter is this lower peak, and that's the resonance of the low pass filter, and the band pass filter is this peak, and that completely goes over quite a short period. And I've misdrawn this because we now feed the two filters with two envelopes. So here we have, I'll make a mess of our drawing. Here we have N1, which goes something like that, and we've added an N3 here, which goes like that, which decays away very quickly. So let's implement that and see if we can get any interesting results out of it. Okay, very quick look at the code. Now the voice mixer now mixes the oscillators together and outputs two values, one controlled by envelope 1 and one controlled by envelope 3. Okay, and here's how the filter's configured. The low pass filter uses the input controlled by envelope 1, and the bandpass filter uses the input controlled by envelope 3, and they're just summed together. So I have just modified the code temporarily so it outputs the envelopes. So let's see what I've done with that. So there are the envelope outputs, and we'll have a look at one note. So this is envelope 1, which is controlling the low pass filter, and you see that rises relatively slowly and decays slowly, and this is envelope 3, which is controlling the bandpass, the input to the bandpass filter, which rises very sharply and decays quite quickly. So now I have temporarily disabled each input in turn, so we can hear what's coming out of each of the two filter blocks. So here we have the one with no bandpass filter, and let's hear what that sounds like. Again, it's not designed to be this wonderful synth patch ever, it's just to demonstrate the principle of what we're doing here. Okay, so now we will look at what's coming out of the bandpass with no low pass. And remember, that was the low pass filter with a very soft attack, and this is the bandpass filter. Okay, so should we put them together? And that sounds like this. And it's important to note that I've turned off the cutoff frequency envelope modulation completely, so the change in tone is entirely caused by the relationship between the output of the low pass and the band pass filter. and the bandpass filter cutoff is increased gradually as the sound file plays, just so you can hear the effect of it. Okay, so what else might we do with our two parallel filters? Well, let's have a look at what we might do if they were both bandpass. And to do that, let's have a little digression into how vowel sounds are made, how the human voice makes vowel sounds. Now, the human mouth and throat, etc., the vocal tract, is basically a lot of, well, not a lot, a few cavities which act like bandpass filters, and these the frequencies of these filters can be altered as you speak or sing, which is how the different vowel sounds are made. And here we have a typical frequency plot of a vowel sound, and here we have Wikipedia's description of it, which is better than mine, so if you want to know more, read that. And here we have a table of various vowel sounds, and it turns out that actually only the first two formants are really vital for telling what the vowel is. And here's a list of a bunch of vowels and what those two formant frequencies are. Now, we are in no way going to try and synthesize vowel sounds or speech. We are designing a synthesizer, but I have merely gone into this to illustrate that the human ear is particularly good at picking up two peaks in a spectrum. Okay, so here we have our filter configured as a bandpass, two parallel bandpasses, and it does precisely that. It calls two bandpass filters. And here is what I've done. It sets up both filters at the start and then plays the first note, and then before each of the subsequent notes, there are 5 notes in all, it sets up the filter 1 cutoff frequency, the filter 2 cutoff frequency, the filter 2 resonance, and the filter 2 amplitude before it fires the note. So each of those 5 notes should sound quite different. So shall we run it up and see what happens? There we go. So let's load that up, and here it is, and let's play it and see what happens, see what it sounds like. Again, no particular musical merit in that demonstration, but you can see you can get some quite different sounding sounds just by changing those filters, and there's no envelope modulation on either filter in this. And if you've been following my build of the mean green, you'll know I've put a joystick on, and I don't know, specifically for this kind of thing, where I can put each corner of the joystick to one of these separate filter configurations and just flip the sound to each different one for groups of notes or different notes. And we will try that once I get that running in the mean green synthesizer. Okay, so that's it for our little look at using two 12 dB for octave filter blocks in parallel. As I've said, this is not something I've implemented, it's just some ideas I've had knocking around for a while, which I thought I'd throw out there and see if anybody was interested in. And I will implement them in the mean green and see what they actually come out like when implemented in a real synthesizer, not just that test program. And next time will, I believe, actually be the final one in the synthesis tutorial, which will be part 3 of the filter enhancements, in which we'll have a look at trying to make a filter which works a bit more like the filter works in a Moog, and we'll see if we can get that to sound warm or fat or whatever you like to call it, having not been entirely successful trying to make our filter as it is sound warm. As usual, all the sound files and the code can be downloaded to avoid YouTube's sound processing, and there are links in the description. So until next time, it's goodbye from Triplicate, home of interesting electronics. Goodbye.